Okay. So today we will discuss proper best change. So we did some computation for italic homology of curves, but for higher dimensional varieties, this method does not work. So we used a computation of the Breuer group of a curve. And, well, for example, what is italic homology of P2? So we don't have any tools for computing this. P2 is two-dimensional projective space. Even this most basic question turns out to be very difficult. And in fact, Grothendieck, developing his theory, got stuck and almost gave up his approach. And so it was Michael Artin who saved him. He proved this result. So what is the general idea for study homology of higher dimensional varieties? Suppose I give you some variety X over spec K. Well, one possible approach is to fiber to decompose this morphism from X to spec K into write it as composition of morphisms. Such that fn minus 1, such that the fibers, every fiber has at most dimension 1, right? Some possibly singular curves. And then, so by what we call Leray spectral sequence, or the language of derived categories, so the homology of X with coefficients in F can be written as composition of derived direct images. So this will be F1, right? So the idea is to use information about homology of curves to say something nice about these derived direct images. Maybe we can compute it. So the tool that we need for this, so we know something about homology of the fibers, and we want to say something about the derived direct image. So the tool is, so this is the main theorem. Well, before I state the main theorem, so let's assume that we have any morphism from X to S. And I give myself another scheme S prime, and I form best change square, X times S prime. So let's say this is F, this is G, and this will be F prime, and this will be G prime. Okay? So I claim that in this situation, I have a canonical map from, so I start with a sheaf F on X. And what I can do, I can take its direct image composed with the inverse image. And on the other hand, I can, oh, sorry, this is -1. On the other hand, I can first take pull back, this is over S, right? Pull back to X times S prime, and then apply this functor. And I claim that, in fact, for any commutative diagram, it need not be even a Cartesian diagram, there is a map in this direction. Well, let's construct it. So how does it work? So let's constructing this map is equivalent by adjunction to constructing this map G low star F prime low star G prime inverse of F, right? So now this composition, so what we have here is, this map is equal to, because my diagram is commutative, it's equal to the composition of J, well, I will write down. This is G prime low star, F low star, G prime, inverse of F, right? And now, if you so use that junction once again, you have a map from F to this guy, right? So this gives me a map between these two sheaves. Is it okay? So this map gives me a morphism from the direct image of F to this, and therefore by adjunction I get this map, which I will call best change morphism. So all we used here is that this diagram is commutative. So replacing these functors by derived functors, so we have derived category of sheaves on AX, we have the derived category of sheaves on S, and we have here the derived direct image, and we also have the adjoint functor. So using this pair of adjoint functors instead of F low star and F inverse, we get the same map for the composition of the derived functors. So mapping derived category. G inverse to F low star composed with G prime inverse of F. And I will refer to this as best change morphism. So let's give a name to this. So once again, it exists whenever you have a commutative diagram of schemes. Commutative square. So now the theorem is that if F is proper and F is a torsion sheaf, and torsion sheaf means that all its stocks are torsion abelian groups, then this map is an isomorphism. Okay? So let's first try to understand what this theorem really means. So let's start with a corollary. Let's take for S prime a geometric point. Dima?
Which sheaves are we talking about, like étale sheaves?
Étale sheaves. Yes, everything is étale. Étale topology. Yes. Okay. So, okay. So suppose I have S geometric point. Then, so the applying this, taking for S prime this geometric point, what we conclude is that the stock of direct image of F, again F is torsion, F is proper. There is canonical map to homology of the fiber over the geometric point. And I can restrict it to XS. And this map is an isomorphism. Okay? So that will be the main tool. So we will at least applying to fibration where fibers are curves and using information about homology of curves, we will conclude something about this higher derived direct images, at least about stocks. For example, that they are finite, if F is finite. Okay, so in fact, corollary implies theorem. Well, we have a morphism in general, functorial morphism. So in order to check that this is an isomorphism, it suffices to check that it's an isomorphism on stocks. And well, we know how stocks behave with this inverse image, and so just applying, taking. So a morphism of sheaves, or even of complices of sheaves, is an isomorphism, quasi-isomorphism, if and only if it's an isomorphism on stocks at every geometric point of S prime. So this is key. Now let's give let's think what this result really means. So so let's reformulate it more geometrically. So what is by definition, or by very general result that we discussed some time ago? So what is the stock of the higher derived direct image? This is something very concrete. So you take, so I will draw a diagram here. You have X, you have S, you have S bar. This is the geometric point. And this map to S factors through the spectrum of the strict Hensellization, kind of well, étale neighborhood of this point S bar in S. So this is S bar. So here I have XS. And this map factor through X, let me call it O, S, H, S, S bar. Now, this guy is nothing else but Qth homology of this sort of tubular neighborhood. X or strict Hensellization of S bar with coefficients in F. Well, I have to restrict it. I'll simplify my notations. And then by restriction, this group maps to homology of X S bar with coefficients in F. And really the assertion, this corollary, which is equivalent to the theorem, is that this restriction map is an isomorphism, right? So really, theorem is equivalent.
Was this in EJ8 where we have that X is quasi-compact, quasi-separated?
Yeah, but it's proper. My map is proper, so it's separated and.
No, I mean, we didn't have a proof of that.
Yes. Yes. So it's, yeah, but this is easy. So you, under very weak assumptions, this is true. So theorem, this theorem, proper Best-Change theorem, is therefore equivalent to the following statement, local statement. Well, not local. So we have a say map from X to S, where S is spec of a Henselian ring, Henselian. And so here I have x0. This is over S. And then, so the really the statement is that homology of X with coefficients in any F torsion sheaf restricts isomorphically to homology of x0. Right? Okay. So, well, before we discuss a proof, let's consider a. So this theorem fails if without the properness assumption. So this map F must be proper. F proper. So what would be the simplest example where it fails? Any what?
A fine line over the-adic integers.
Well, that's too complicated for me. The simplest example, I think, would be the following. You take for x, s minus s. This is an open embedding. Then this guy is 0. But take the constant sheaf and 0 derived direct image. All right? Fails. So, well, this theorem is also true in algebraic topology. Well, it's true for topological spaces. So let me formulate this. So proposition. So let. Сейчас будет селективно. Сейчас. Через секунду. Теорема неверна.
В смысле, чего?
Ну, да.
Типа ее нет. В смысле...
Нет, ну в смысле, это отображение не собственно. Открытое вложение — это не собственное отображение.
Но как бы тут...
Для каких случаев оно верно?
Для собственных. F proper.
Вложение x без точки. Все, я поняла. Ладно.
Ага. Okay. So let x f be a continuous proper separated map of topological spaces. And let's say I have a point. Then, so then for any sheaf F, not necessarily a torsion sheaf. So what is a proper map? Proper means that it's closet, image of closet set is closet, and fibers are compact. And separated means that the diagonal is closet, so for Hausdorff spaces. Okay, so then for any F, the map from R F rho star of F at point S to homology of the fiber is an isomorphism. Okay, so kind of I will not give a proof, but I will maybe give a kind of try to explain what's going on here. It's not a difficult statement. It's easy statement. I will not use it, so not spend time on this. So the idea is that so you have x, you have x0 or xs. So xs is itself compact, and then so for so you can check that that this guy here, homology of xs, homology of xs with coefficients in f, is equal to the limit. So I take any sheaf on X and I restrict it to a compact subset, closed subset. And then the claim is that this cohomology group is equal to the limit over all neighborhoods, open neighborhoods in X of cohomology groups of U with coefficients in F. Okay? So let's believe to this. It seems reasonable. And now the observation is that when you map to S is proper, then a fundamental system of neighborhoods, right? You can consider all kind of neighborhoods here. This is S, formed by sort of cylinders. You can consider for U the following neighborhoods. You pick a neighborhood of point S in capital S, and you take its open preimage. This is kind of a cylindrical neighborhood. If this map were not proper, of course you can have something smaller neighborhoods, such U that do not contain any cylindrical neighborhoods, right? Using properness, you can show that any U contains a neighborhood of this type. So you take a full preimage, right? So, and therefore, this limit is equal to the limit of the cylindrical neighborhoods, and this is by definition the stock. Ну как? Ну надо взять, у каждой точки существует окрестность. Но пусть у меня есть точка, и у нее окрестность. Я могу эту окрестность взять такую как бы... Да, очень замечательно.
Подозрительное утверждение. Если мы возьмем f, просто тождественное отображение.
Да.
Вы утверждаете, что когомологии точки это всегда предел когомологии маленьких окрестностей?
Но это же слой в точке.
Ну, легко придумать пример, нарисовать такое топологическое пространство, у которого в любой окрестности точки нетривиальный когомология.
Да, но мы считаем когомологией пучка. Если неправда, что когомологии постоянного пучка это то же самое, что когомологии, вот сингулярные когомологии, как они определяются. Если вы их определяете как когомологии пучка, то это будет всегда верно.
Какие когомологии постоянного пучка в этой серии?
Ну да. Ну в смысле, что вот такой предел будет нулевой. Что вот вы берете любое топологическое пространство, берете точку, берете когомологии окрестностей этой точки с коэффициентами v. Всегда получите 0, предел. Но если бы вы по чеху считали, то это было бы очевидно. Но это верно всегда. Вот. Доказательство, но оно занимает полстранички, оно есть, например, в книжке Stacks Project. So here is one more example when this that shows what may goes wrong when the map F is not proper. So take for example, C, and take S1 times C, and remove 2 points. So A, 0, B, 0. This is the projection. Then, and let's just look for zero cohomology. Zero cohomology, the fiber over the origin is not connected. So zero homology of the constant sheaf will be two-dimensional. However, if you consider any tubular neighborhood of the special fiber, it's connected. Right? So yes, so if I remove 2 points from S1 times an open neighborhood of the origin, right, it's still connected. So that means that the stalk will be still one-dimensional, but the fiber is two-dimensional. And this is exactly the example that where this system of tubular neighborhoods, tubular neighborhoods do not form a cofinal system among all neighborhoods of the special fiber. Okay? Да.
Что двумерно? Когомологии слоя.
Да, когомологии слоя двумерные.
Слой двумерный, но при этом на базе одномерный и на всем
Да,
тоже.
да.
Вообще, что-то я как немножко потерялась. У нас была теорема
Да.
про base change. Мы ее свели к факту про генерализацию, да?
Да, да.
Мы свели к теореме штрих.
Да.
Святой локальный.
Да, да.
А дальше мы не доказывали.
Не доказывали, мы сейчас будем ее доказывать. Это топологический аналог. Аналог этого утверждения в топологии. Он не будет использоваться в доказательстве и является исключительно мотивировкой. Ну, здесь не важно. Это утверждение, с одной стороны, нам достаточно знать для строгой Гензелевых, чтобы вывести теорему, но с другой стороны, по теореме, наоборот, это верно и для строгой Гензелевых.
Почему вложение? Генерализация строго вложение у вас?
Ну, хорошо, отображение. Да, отображение. Я не знаю, что такое отображение. Окей. Да.
В конце концов, даст типа изоморфизм сравнения. Если я многообразие мог поднять над векторами вид,
например. Там вот эта теорема специализации, она состояла... Давайте, может быть, можно мы этот вопрос обсудим чуточку позже. Сейчас мы вернемся, сейчас мы будем обсуждать фундаментальную группу и специализацию, потому что как бы доказательство этой теоремы, оно использует то, что мы доказывали для фундаментальной группы. Тогда, может быть, будет чуточку понятнее. Хорошо? Okay, so let's start proving this. Maybe before I give a proof, let me show you a simplest application of this proper base change theorem. So I told you that so far we don't know how to compute homology groups of even simplest two-dimensional varieties, like P2 or P1 times P1. Let's use it to do this. So let's prove Kunit formula. Kunit formula. Well, that's not the most general form of it, but it's a good illustration. So I'm interested in the following situation. I have X and Y. They're schemes over algebraically closed field. And I want to compute cohomology of X times Y in terms of cohomology of X and Y. So is in algebraic topology, unless you work with coefficients, with coefficients in, look at homology with coefficients in a field, you have some torus derived tensor product in the statement of the Kunit formula, right? If you look, for example, for homology with integer coefficients, it's a bit. Well, the best way of stating it is also using use derived language of derived categories. So here is the statement. So let's consider R gamma of X times Y with coefficients in a, say, in constant sheaf. This is a complex of Z mod and Z modules. And then, so the claim is that, so if that this is R gamma of X with Z mod and Z coefficients, tensor over Z mod and Z, well, since I work with the derived category, in derived categories, the only assertion that makes sense is to take the derived. Well, I am forced to take the derived tensor product because this is well defined only up to quasi-isomorphism anyway. And then, so that's the assertion. Unfortunately, this assertion is false unless you assume that X or Y is proper. In fact, it fails for X and Y being A1. We computed homology of A1 of a scheme with Z mod PZ coefficients. For affine schemes, these are just functions modulo the co-kernel of the Artin-Schreier map on global functions, and you can see that the statement for H1 is not true for A2. So nevertheless, there is another argument that shows that it's true if n is invertible in the ring of functions on X. So For A1, it's OK, provided that you look at homology with Z mod and Z coefficients where n is not divisible by p. But this requires a separate argument. OK? So let's prove this. So proof. OK. I think I want to write it here. So maybe just a remark. So in particular, this Kunet formula implies that homology of P1 times P1 is what you expect. So here you have this derived tensor product, but if you know that homology of x and y with Z mod and Z coefficients are free over Z mod and Z, then you can replace the derived tensor product by the usual, right? So, and you recover the usual formula, as in the case of fields. Or if n is prime, then you also, is a prime number, then you also do not need all this derived stuff. But the proof in the language of derived categories is especially simple. So let's take x, y, and you look at the projection f to y. That's a proper map. And here I have pi, which is a map to spec k. Right? Then, so I have a map from the constant sheaf. So I take R gamma of y, of x with coefficients in Z mod and Z, right? I think of this just as a complex of abelian groups of Z mod and Z modules. This is a sheaf on spec K. K is algebraically closed, so the derived category of sheaves is just the derived category of abelian group, or Z mod and Z modules. So abelian groups. So this is a constant sheaf on Y. And I claim that there is a map from this constant sheaf to F R F low star of Z mod and Z. Right? So how does it work? Well, by adjunction, constructing this map is equivalent to constructing the map of complexes of abelian groups from this complex to R gamma of x times y, Z mod and Z, right? So if you take R pi low star composed with R F low star, that's the same as R gamma. Yes? Ну, потому что глобальное сечение — это композиция вот этих двух прямых образов. Да? Это, опять же, формальность. Значит, okay, so I do have such a map, which is given by this projection. So let's call it G, and then G inverse, the pullback, gives me this map. And by adjunction, it gives me this map. And now, now we use proper base change theorem to check that this is an isomorphism on stocks. The stock of the constant sheaf is just this. The stock of this is homology of the fiber. Okay? So that's gives me this isomorphism here. So, okay. And now, we have the formula follows because so I need to use the following general assertion that homology R gamma of Y with coefficients in any constant complex, right? C here is a complex of sheaves, but constant. So it's just a complex of abelian groups. There is a universal coefficients formula that's the same as C tensor with R gamma of Y with Z mod and Z coefficients. So you take this formula here, you apply functor R gamma, and you sort of move this out and recover the assertion.
So we need that if we have a constant sheaf, then it has an injective resolution by constant sheaves.
Yeah, so a very nice, well, you're asking about the proof of this. So there is, as in classical topology, there is something called Godemont resolution, which is very good for proving this type of statement. So you embed your sheaf into direct product of sheaves of stocks, right? And every stock is considered as a sheaf supported at one point. These sheaves, well, need not be maybe injective if your coefficients is not an injective abelian group, but it's acyclic in the sense that it doesn't have any higher homology, right? So you can produce a canonical resolution for any sheaf, this Godemont type resolution, and then you can use it to prove this assertion. Good. So okay. Now let's go back to the proof. So proof. Okay. So first, I want to, so step one. So we are proving, what we are proving? We are proving, is it still here? Yeah, we are proving this statement here. And so step one will be Q equal 0, and F is constant. Already in this case, the theorem is non-trivial, and it amounts to the following proposition, which is due to Zariski. Very well. Okay. So A is Noetherian. Henselian. Ring. So S is spec A. And then we have map from proper map from X to S. And the claim is that this map so induces. So we have the special fiber and we have the generic fiber. I want to compare zero homology of the special fiber with Z mod and Z coefficients. This is a free abelian group spanned by connected components, generated by connected components of x0 and of x. So this theorem in this case amounts to the following, that the embedding induces bijection on connected components. So if X is connected, then the special fiber is also connected. So it's not, well, this is very useful in birational geometry. Well, it's, что вот это, что это, okay, so let's give a proof. In fact, we proved this, but the argument is so nice, and it was a long time ago, so I want to repeat it, just to refresh. That also explains, in the simplest case, the technique that is used here. Это специальный слой. У меня S — это локальное кольцо. Вот. Ну вот, в том примере, который, в топологическом, правда, примере, ну, я там выбросил две точки из S1. Вот. X0 стал не связанным, а X остался связанным. Okay, so proof. Well, what is pi 0? What is the set of connected components? So, the finite subsets of the set of connected components are in one-to-one correspondence with idempotence in the ring of global functions on X0. So really, what I want to show is that idempotence here, or X, there is a restriction map to idempotence on X0, that this is a bijection. That's what we want. So what do we know about these guys? So maybe I will write it here. Oh, that's what I will use. So gamma X or X is a finite A algebra. And therefore, it's a product of local algebras. Right? So because A is Henselian, so it's finite because the map is finite. The map is proper. And so one of the definition of a Henselian ring was that any finite algebra over a Henselian ring is product of local. Now, okay. So, and therefore, idempotence here is the same as idempotence of gamma X or X modulo the maximal ideal. So here M is the maximal ideal in A. Yes? Right? Because every closed point maps to closed point of spec A. So, right? Now, unfortunately, yeah, is it okay? Ну, допустим, что это утверждение про конечные алгебры над Гензелевым кольцом. Допустим, что у меня есть локальная алгебра. Ну, она по модулю максимального идеала, она связана. Но она тоже локальна. А любая алгебра есть произведение локальных. Значит, я утверждаю, что... Да, хорошо? Угу. Okay. So, unfortunately, there is no immediate relation between this guy and this guy. However, well, there is a kind of base change theorem which is much easier than the one that we discussed for coherent homology, but it involves some derived standard products, and well, the relation is complicated. However, there is something, well, the idea is to consider idempotence in another algebra, which is the completion of this. That's a finite algebra, so it's the same as completion. Okay? So you still have this. And now this algebra can be related to the one that we have here. And this is known as the formal function theorem. So I'll maybe state it here. So formal function theorem is the following assertion that the limit of gamma x or x, the completion of this limit over n, that's the inverse limit, is the same as limit of gamma xn or xn. So here, well, I have x, I have x0, which is the special fiber, and I have nth infinitesimal neighborhood. So it's not true what you could expect, that this guy is just equal to this. This is not true in general. But when you pass to the completion, when you pass to the limit, it's true. This is proven in Harshhorn book. So, well, now, in particular, since idempotence in all these guys are just idempotence in x0, right? These are nilpotent thickening, you get the result. Mm-hmm. So this proves the assertion. Okay? So even in this simplest case, the proof is non-trivial. It uses some math, namely this formal function theory. By the way, the proof of the formal function theorem, well, it amounts to showing that you don't have the derived inverse limits here. So this satisfies Mittag-Leffler condition, which itself follows from finite dimensionality. It's not a, well, very difficult result. The risky proof was complicated. Okay, now let's see what we have for q equal 1. So step 2. Still q equal 1, and f is z mod n z. Okay, so then h1 of x with coefficients in z mod n z classifies z mod n z torsors. over X. So these are finite étale covers over X with action of Z mod and Z that make it a torsor. So really, the theorem in this case follows from the following assertion that the category of finite étale covers on X is equivalent to the category of finite étale covers on X0. So if you have Y over X, you can assign to it X its restriction. Okay, X0. So remember that X is over a Henselian ring, and X0 is a special fiber. So once we know this key statement, we know the theorem for H1. So do we know this? Well, so what we proved, we discussed theory of fundamental groups. And we proved that this is OK for complete Henselian rings. That's precisely the assertion that we proved. Right? We proved that the fundamental group of X is the same thing as the fundamental group of X0, well, for connected X0. So now the general case is derived from this using what's called Artin approximation. Okay, so let's see. So the injectivity, the fact that so fully faithfulness of this functor follows from the risky theorem. What really this theorem kind of what it really tells you new is that any cover of X0 can be extended to cover of X. And so we know that, so if I have A, I can think of this as a subring of completion. Maybe I also assume that A is Noetherian for safety. A Noetherian. Because otherwise, I may not have this embedding. All right? That's Krull theorem that I have embedding. So, OK. So what Artin approximation theorem tells you is that so if you have a system of polynomial equations with coefficients in A and a solution to this system in completion, then there exists a solution in A which is equal to the formal solution here, modulo any prescribed power of the maximal ideal. That any solution in the completion can be approximated by an algebraic solution. Right? So here is, this is a, well, that's kind of tricky result, which I will not prove. Let me explain how you use it. So, so I give myself a cover over X0, and by this, by what we already proved, it can be extended to a cover over this guy. finite étale cover over the completion, right? Every finite étale cover over the completion is actually defined over some finitely generated ring, right? So that means that I can produce a finitely generated ring, a map like this, such that, so I start with a cover over x0, then I construct a cover over this guy, which is actually defined over some smaller ring. Any cover is defined over some smaller ring. And then, so my goal is to produce a cover over A, which lifts this cover over x0. And so what is this map? So A prime is z of x1, xn modulo some polynomial equations, f1, fm. And producing this map, well, this map is the same as just given collection of elements here satisfying these algebraic equations, right? And using the Artin approximation theorem,
So we're looking at an étale cover of spec A.
yes. So we start with an étale cover over x of x0. We first use this theorem, this part, to produce an étale cover of x spec A hat over A, right? Then we descend it to some finitely generated ring.
So we need to either put A here instead of Z, or we have to bid some model of X over Z. Otherwise, I don't think it makes sense.
That's a very good point. Very good point. Okay? Thank you. Okay, so we have such a map. And by Artin approximation theorem that I stated but I didn't write, there exists a map in this dotted arrow such that, well, I'm not saying that any map from A prime to A hat factors through A. This is not true. But they become equal when you project it to A modulo the maximal ideal, or any power of the maximal ideal, right? So there exists this dotted arrow so that if you go this way, it's the same as if you go this way. So we have a finite étale cover over A prime. Yes? So x times A prime. But then this map gives me a map from x to this guy, right? That's given by this dotted arrow. So I have a finite étale cover over this, and I can construct from this a finite étale cover over x. Okay? That's the strategy. But again, the main content here is this Artin approximation theorem. It's a statement about polynomial equations, property of Genselian rings.
So this is the first time, so first we have to go beyond EGA.
Yes. So this, well, the proper base change theorem is really the most difficult theorem in kind of general theorem in étale homology, and it's proven in SJ4. The proof is very long, complicated. Then Artin simplified the proof. He proved this result about polynomial equations. So the proof that I'm explaining here is, well, essentially it's written in SJ4.5, but it's sketched there. So details are in text project or, well, maybe somewhere else also. Okay. Oh, also, in fact, text projects say that Artin also has rewrote the proof using his approximation theorem, and it's also very concise and readable. Okay, so now this is the case when Q is 1, constant coefficients. So let's see what else do we have. So some reduction. So step 3, easy reductions. That's okay. Theorem is true. Is true for finite f, right? So for finite f, that's very simple, because x itself is direct product, is disjoint union of Genselian local rings. So there are no higher homology of sheaves on let's see, theorem is true for finite f and right. So how should I say it? So homology of Genselian rings of any sheaf on Genselian ring is the same as homology of this sheaf restricted to the closed point, right? So, and therefore, the theorem kind of holds trivially, just from the structure theorem again, that X is itself direct product of Genselian rings. If you are uncomfortable, maybe I'm skipping here a step. So think of that S is strictly Genselian. It suffices for our application. So that's S is strictly Genselian. Then you don't need, you don't have higher homology. You have just H0. Genselian. And we show that global sections are just the fiber. Strictly Genselian. Okay. So step 4 is if you have x, y, z, sorry, if you can decompose it into the product of morphisms. And if you know the theorem, if theorem holds for f and G, then it is true for the composition. F composed with G. Okay, so this is trivial. What is less, what requires a little bit more work, but. Что? Да, для всех пучков. Okay, so, and what requires a little bit more work, but also kind of formal. So suppose you also have such a diagram. This is F, this is G. So here I assume that F is surjective. So, and then this assertion that the theorem for F and the composition G, F, implies the theorem for F for G composed with F. G composed with F. I will omit this. It's formal. So now, сейчас, простите. Правильно? Okay. Спасибо, что следите. Okay. So step 5. 6. Enough to prove theorem for x equal to p1 times s. That's surprising. So let me explain this. Ну, мы сейчас будем использовать одно упражнение из первого листочка. Okay, so here is the argument. So let's take x. So I have morphism to S. This is proper. S is Genselian spectrum of Genselian ring, in particular it's affine. There is in this situation we have Chow lemma, which says that this map for any proper scheme over S, there exists a projective scheme, x prime, where this is proper birational, surjective, and this is projective. So that means that I can factor it inter Pn times S over S. So, okay. So first of all, I claim that it's, let's first show that if I know this, I know the assertion for Pn times S for higher dimensional projective space. And here is the argument. So remember that the symmetric power and symmetric power of P1 is isomorphic to Pn. In particular, I have a finite surjective map. Finite surjective. Okay, so now let's use steps 4 and 5. So if I know the theorem for P1, I also know it for products of P1 using step 4, because I can factorize this projection to S to interproduct of projections with fibers S, P1. Then, right? This map is finite and surjective, so I know the theorem for finite maps. Okay, so we know that this implies the same assertion for Pn. Now, it follows this map is a composition of a closet embedding, which is a finite morphism, with the morphism for which the proper base change is known. So we have it for x prime. But this map is projective, right? So it means that you can also factorize it as P maybe some m times x. And this is a closet embedding. Okay? So by similar argument, we know the theorem for this map. So now we know the theorem for this composition, for this map, and this is surjective. So we know it for this.
Сейчас, а для этого персонального вы поняли, потому что мы знаем, что две композиции.
Вот для этого бирационального. Ну, потому что оно, да, потому что просто мы знаем теорему для этого отображения, потому что это замкнутое вложение, в частности, конечное. А это, ну вот мы здесь такое делали. Very good. So it's enough to prove the theorem for P1. And here is one more step. Okay, I want to finish. So I will have to skip another kind of formal argument. Okay. So let's see what I want to prove. So this is step 7. Okay, and so step 7 is the following proposition. Suppose I have any scheme X and X0 is a closed subscheme, and assume that for all n greater or equal than 0, and all finite x prime over x, the following holds. Homology, the map from homology of x prime with z mod and z coefficients to homology of x0 prime with z mod and z coefficients. What is x0? So x0 prime is x0 times x prime over x. That's the restriction of my finite cover, is isomorphism for q equals 0, and surjective for q greater than 0. Then for all torsion F, this map from HQ of X is F. The restriction map is an isomorphism. Okay? This is kind of diversage argument. So you first reduce to constructible sheaves, then you reduce to local systems, and then you trivialize local system after some finite covers. And well, it's pretty formal, though it's very nice. And now we finally, so assuming that this is true, we finally reduce everything to the following key lemma. So step 4, step 8, and this is the key lemma. So key lemma is the following. So F is x to spec A is Henselian. Strictly Henselian. Noetherian. And so this is F is proper, and dimension of x0 is less or equal than 1. So then the restriction map from homology of x with z mod and z coefficients to homology of x0 with z mod and z coefficients is isomorphism for q equals 0 and surjective for q greater than 0. So why this q lemma implies what we want? So we want to show the theorem for P1. We use this proposition. Every cover of P1, finite cover of P, well, not necessarily tie, every scheme finite over P1, it projects to spec A and has this property that the fibers are one-dimensional. So, and this is something very concrete. And this is very nice. And it's not only very concrete, we almost have the result. So let's see what we know. So proof. This is OK for q equals 0 and 1 using the steps that we already did, right? And but still it's complicated. It uses this Artin approximation, the results about the fundamental group that we had. So it requires a lot of work. And also empty for q greater than 2. Because this is a curve over an algebraically closed field. And homology of a curve over an algebraically closed field vanish in degrees greater than 2. So surjectivity means nothing. So the only thing that requires a proof is case q equal 2. And this is also something very concrete. Because remember that we have a map from the Picard group of X to H2 of X with coefficients in mu n. Well, I can replace, because I can replace, so I will sort of, I need to consider two cases. When characteristic, when n is divisible by characteristic, and when n is not. My time is very short, so I will consider the most interesting case, the one that will, the argument for when n is a power of this characteristic uses Artin-Schreier sequence, and it's easier than this. And it's not that interesting because we will not be looking at the homology with coefficients in Z mod PZ. So we have this map which comes from the Kummer exact sequence, right? So remember that so mu n is a constant sheaf on A, right? Because residue field is algebraically closed, n is relatively prime to characteristic, so that means that all roots of unity are in A. A is Henselian, strictly Henselian. The equation x to the nth power equal to 1 has no multiple roots modulo maximal ideal, so they're all in A. So, OK, so here I have this map. And what we have, that's also from Kummer exact sequence. And what we proved about this map is that it's surjective. So this is the restriction map. This is also the restriction map. And to complete the proof, it suffices to check that this map is surjective. Now, OK, so all we have to prove is that in this situation, in the situation of the Q lemma, any line bundle on x0 can be lifted to a line bundle over x. And OK, I will do this in 3 minutes. So OK. So peak x to peak x0 is surjective claim. OK, so what we proved is that we look at Schwarzschild divisors effective Cartier divisors. What is an effective Cartier divisor? It's a subsheaf of the structure sheaf which is locally free of rank 1 by definition. So it's enough to prove that this map is surjective. Remember that our schemes are not, though the fibers are curves, but they're possibly singular curves, so you cannot work with Weyl divisors. You need to work with this. So these are effective Cartier divisors, so that's what we want. OK, so suppose I have a divisor D, and I want to show that it can be lifted. So I may assume that support of my divisor, D, is just one point in X0. Closed, well, one closed point. So given, well, locally by some equation, T0 equals 0, where T0 is an element of the local ring. So again, Cartier divisors are just closed subschemes such that the sheaf of ideals is locally free of rank 1. So my closed subscheme is X0. It might have some nilpotence, but it's given by one equation locally. And so pick open neighborhood C in U in X and a lift T in O of U of T0. So consider just the closed subscheme given by equation T equals 0. So Y in U will be a closed subscheme given by equation T equals 0. So the problem is that Y need not be closed in X, right? It's closed only in U. So, but Y over S is quasi-finite. Finite. It's quasi-finite over strictly Genselian ring. So using compactification, every quasi-finite map is an open embedding composed with a finite morphism, and every finite morphism over strictly Genselian ring is disjoint union. Finite ring over strictly Genselian disjoint union of local rings. So we can write Y as Y1, Y2. OK, so maybe I should say here two more words. So I may assume by shrinking U, I may assume that Y does not intersect X0. Well, the intersection is just one point. Yes, otherwise I replace this U by something smaller. Then, so Y1 is finite, and Y2 does not intersect X0. Now, shrinking U, we may assume that Y is equal to Y1. And that's, we are done. So now I define the lift. Set d over x minus y is empty, is 0, and d over u is given by its divisor of t. This gives me a Cartier divisor that does the job. Okay. So that's all I want to say about the, well, proof of the proper base change theorem. So the main step that I didn't say anything about is this Artin approximation result, which is, I don't know, well, I try to understand the argument, but it's complicated commutative algebra. Okay.